All right, we are in Unit 5, Lesson 10, Domain and Range Part 1. Take a look at this warm-up here. This is page 106. And just read this guy, answer these questions, talk with a neighbor, see if you agree, and pause this video, and then unpause when you're ready to see what I think about this warm-up. Okay, hopefully you've paused and had a little discussion. We're talking about the number of times a dog has barked as a function of time in seconds after its owner tied its leash to a post and left. Less than 3 minutes after he left, the owner returned, untied the leash, and walked away with the dog. So we're going to decide, could each value be an input of the function? Be prepared to explain your reasoning. Notice time in seconds. That's an important part of this here. We're going to say 15 seconds. Could we measure how many times a dog barked in 15 seconds? Yeah, I think this is fine. How about 84.5 seconds? That's about not quite a minute and a half. So yeah, I think we could measure. This could be an input, and we can get an output of it, is kind of what we're asking here. Could this be an input? Yes, 15 seconds makes sense as an input. 84.5 seconds makes sense as an input. Now, 300 seconds, 3 minutes is 3 times 60 seconds, so that's 180 seconds, which is less than 300. So that means this 300 is not going to fit inside of that 3 minutes. So this one, no, does not make sense as an input. It wouldn't fit inside of that 3 minutes. Let's check these outputs here. So the first one were inputs. Does this make sense for seconds? Outputs, does this make sense for barks? So could there be 15 barks? Sure. In 3 minutes, 15 barks. In 3 minutes, does 84.5 barks make sense? Not really. We don't really do half of a bark. Be prepared to explain your reasoning. Oh yes, okay, here we are. 300. Could the dog bark 300 times in 3 minutes? I guess it's possible, but that's 100 barks every minute, which I guess it's possible, but not likely, because 300 barks, 100 barks per minute, that is a lot of barks. So anyway, not super likely. Let's go ahead and move on. We're not going to do the next activity, which is the card sort. We're going to go straight to page 108, which is what about the outputs. Go ahead and read this over on your own. See if you can kind of work through some of this on your own, and then when you get stuck or when you're all done, come back, unpause the video, and I'll walk you through it, and we'll do a little discussion here. One-sided discussion? Yep. Pause. Okay. So this is something, we didn't do this square representing tennis match or whatever. That was the last thing. You don't need that though, it's fine. Here's a graph that represents function A. Here's function A, where a of x equals x squared. So you might also see this y equals x squared in the future, just so you can see that. Here's your y-axis. Here, x is the side length of the square in centimeters. All right, so if I were to have a square, if the side length of the square is 1, and then we want, here's a graph that represents this, where x is the side length. So if x is the side length, if 1 is the side length, 1 times 1 is 1, x squared. So this point right here is 1, 1. And then let's go ahead and do, let's just look at 2 and see if that makes sense here. 2 is right here, so 2 squared is 4. So that looks a little low for 4. If this right here is 5, that looks a little, but it's okay, it's fine. Let's move on. Let's look at 3. How about that? 3 squared is 9. So 3 here, that's 9. That feels like it should be up here a little ways farther too. Let's keep moving. Name 3 possible input-output pairs for this function. Oh, did we just do that? If we put f of 1, that gives me 1 squared. So f of 1, 1 times 1 is 1. The number that we put inside here, remember, is the x value. And the one that we end up with out here, remember, is the y value. So 1, 1 is a pair. Let's instead of doing 2 and 3 like we just did, well, let's go ahead. Let's just do 2 and 3, that's fine. So that'll give me 2 squared. F of 2 is 2 squared. Remember, that's the x value inside there. 2 squared is 4, so f of 2 is 4. So I have a point that is 2, 4. The x value is always on the left, y value on the right. Let's look at 3. F of 3 equals 3 squared. F of 3 equals 9. 3 times 3 is 9. Remember, the x value is the one in there, so that means that my x value is 3, my y value is 9. We described a set of all possible values of a, remember that's the y value of the function, as any number greater than or equal to 0. So we can see that here. Here's 0, and notice the y values, or the values of the function a here, just go up. They don't go back down underneath here. They only go up. Now, let's check this guy out. How would you describe the set of all possible output values of a? Oh, did I just do that backwards? I'm sorry. Input, read this better, Mr. V. The input values are the x values. So notice how we start here at 0. Inputs are the x values. So as long as I go to, they don't go to the left at all. I don't have a -1 here in my x values. I only have positive x values. So all of your input values are greater than 0. And as I said, kind of backwards, my output values, notice, those are my y values there. Those go only greater than 0. We don't have anything that's less than 0 here for our output values or for our input values. How would you describe? And that's what I would say. I would say the same thing. Any number greater than or equal to 0. Now here's, well, yeah, that's fine. We're going to say the same thing. Any number greater than or equal to 0. Any number greater than or equal to 0. Because that's our y values going up. That's the output. All right, let's go ahead and move on to the, oh, we're going to flip over the page. Activity 2 continues on the next page, 109. Function r is defined by r of x equals 40x, where x is the number of campers. Is 20 a possible output value for this situation? So thinking about output here, paying attention to that better than I did on the last question. So that would mean that 40x would have to equal, this would be 20. That would be my output. So can I get a number of campers for x to get me 20? And I can just check what that number would be by solving for x. So I divide both sides by 40, and I get 1/2 equals x. 20 divided by 40 simplified is 1/2. Can I have half a camper? No. So that's not going to work. We're not cutting anybody in half. How about 100? Can 100 be an output value? Let's just do the same thing. 100 equals 40x. Divide both sides by 40, and I end up with 10 over 4. My x value, 10 divided by 4, that's 2.5, right? 2.5. No, I can't have 2.5. No, explain my reasoning. I'm not cutting anybody in half. Those aren't the campers we're looking for here. Here are two graphs that relate number of students and camp revenue in dollars. So this is kind of, going along with what we just looked at. Which graph could represent the function? Notice this one, you can choose any point on this line and you've got a y value. Now notice, that means that if I have 5.5 campers, I can get an output there. Can I have 5.5 campers? No, I can't have 5.5 campers. This one, I've got 5, 6, 7. I've got all integers, a regular number of campers where nobody gets cut in half. So the only one that is going to work here is this one on the right. Which graph could represent R? These are not labeled that I can see here. So this guy here is the only one that can then actually represent this in a real life situation. And I've done that explanation here. You should write something down about not cutting students in half or thirds or whatever. Describe the set of all possible output values of R. So for this one, we ignore this guy because this is in a real life situation. This one is here. So what we're going to do is we're just going to look at each x value, which is the number of campers or number of students. And then we are going to, okay. Anyway, and then we're just going to see what is the y value there. And we could actually use our formula if we wanted to, because some of these don't really match up very well. It's a little bit hard to see where those land. So we have our x values. Let's make a table. How about that? We put our input on the top, which is x, number of students, and then we put r of x or y on the bottom, which is the revenue in dollars. So we're going to do 5, 6, 7, 8, 9, 10, all the way through 16. All right. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And don't worry, we're not going to have to do a whole lot of math here. Once we see a pattern, we're going to be able to just fill in this chart pretty easily. Remember, our function is r of x equals 40x. R of x equals 40x. So if I were to plug 5 in for x, this one is pretty clear. 5 times 40 is 200. So that one's 200. I should have left myself some more room in those little boxes. Oh well. If I plug in 6 for x, 6 times 40 is 240. 7 campers, 7 times 40 is 280. Now you might see the pattern. I'm just adding 40 every time. So this should be 320, 360, 400, and I'm going to stop right here, double check and make sure what I'm doing is right. If I plug in 10 here for x, 10 times 40 is 400. Okay, so I'm on the right track. Add 40, 440, 480, 520. Let's see, next one is 560, 600. 40 times 15 is 600, yep. And then 660 for 16 campers. So that's how you do C. And that is my description right there. I would use all of that for my description, that's fine. Activity 3. Here is another kind of function. That is a weirdo looking function that we have, but we're gonna use it. To find the sets of possible input and output values of the function, Claire created a table. This looks so much like the table that we just created on the other one. Evaluated f some values of x. Along the way, she ran into some trouble. Dun dun dun. Let's do what Claire did. All right, let's plug in these values here for Claire. So let's go ahead and plug in negative 10. So for the first one, we're going to go 6 over negative 10 minus 2. That gives me 6 over negative 12, which is negative 1/2. So for negative 10, our output is negative 1/2. That looks fine. That doesn't look like there's any kind of problem with that. Let's plug in 0 now. 6 over 0 minus 2. That gives me 6 over negative 2, which is negative 3. That doesn't look like a problem to me. 1/2. All right, so I've got 6 over 1/2 minus 2 equals 6 over, that's negative 1.5, which is 6 divided by 1.5 is 4, right? Let's see, 6 divided by 1.5. Uh-oh. Yeah, it is 4. Good, I'm right. And that should be negative 4, because that's a negative on the bottom, a positive on the top. Negative 4. All right, let's plug in 2. Let's see what happens with this one. Oh, I have a bad feeling about this one. X over 2 minus 2 is 6 over 0. Uh-oh, dun dun dun. Hopefully you remember in your class that when I have a 0 on the bottom, then I have, this is called undefined. So this is undefined. 6 doesn't get to be in the denominator, and we'll probably talk about that in a bit. Let's plug in 8 though as well. 6 over 8 minus 2, that's 6 over 6, which is 1. That one is fine. So your trouble here is this one. That's Claire's issue right there. When I plug into undefined, which means I don't have an output for this input. Or, yeah, something bad's happening. Use graphing technology. What do you notice about the graph? Use graphing technology and figure it out on your own. Should we do that? Should we go do graphing technology right now? Maybe we'll come back to it again in a second. Use a calculator to compute the value you and Claire had trouble computing. What do you notice about the computation? All right, we might go graph this in a second, but let's do number 3 since I'm sitting here. What do you notice about the computation? So what they're asking here is what's 6 divided by 0? Notice it says divide by 0 error. There might be some other kind of errors that you see in there, but there's a problem with dividing by 0. What could you describe, how would you describe the domain of the function? Let's go ahead and, so notice you haven't seen anything about domain here until the lesson summary. You'll see domain and range in the lesson summary. Domain is that the included, the x values that are included in the graph. And so we'll talk about that in a second. Let's go, let's graph this thing. And then we'll talk about it. So I guess we'll just go over here. We'll go into Desmos. We'll graph this thing. All right, let's go ahead and let's go to Desmos. So go to desmos.com. That's the best way to graph this stuff. And then go down to graphing. And then we're just going to go ahead and graph. Look, we're all set here. We're going to plug in these values. We're going to plug in this function, and we're going to see what that looks like. All right, so let's go ahead and go. We need a y equals, I believe. Yep, and then we're going to go 6 divided by, which is, I think we could just do it with this guy right here. Yep, that worked fine. And then I'm going to do a little parentheses. I'm not sure if I need it or not. That is x minus 2. X minus 2. And I'm going to close my parentheses. There we go. So it should look like that. That looks good. All right, here is, whoa, look at that graph. That's something that we haven't seen in this class before. This is what it looks like. So here we've got these values coming from almost at 0 on the y-axis. I mean on the x-axis, sorry. Well, okay, let me cut that back. This goes closer and closer to the x-axis, which is y equals 0. And then it goes down, vroom, like that. Notice this one goes from infinity way up in the stratosphere, farther than, infinity. Then it comes down here and it goes, look how it hugs the x-axis again. This is never going to touch the x-axis here. It's never going to touch the x-axis on either side. It's just going to go on forever in both directions, never touch the x-axis. The other thing it's never going to touch is right here. There's something called an asymptote right here that is between these two pieces. This is going to go down forever and ever. This is going to go up forever and ever. And it's never going to touch something. And that something is right here. Notice how it's undefined here? This is where x equals 2. So right here, in between these two guys, that is x equals 2. And I left my pencil over there, so I'm going to just write. Use a graphing technology. What do you notice about the graph? Notice that it looks like this. And there is a line right here that isn't showing on the graph. I mean, they don't have a line showing right there. You could probably make it do that, but I don't know how to do that. This line is called an asymptote. Asymptote. I think that's how you spell it. Now I'm on YouTube spelling things wrong. X equals 2. Calculate, yep, and that looks it. So how would you describe the domain of this function? So that's the last thing we want to do. And I'm going to go ahead and move back because we have drawn a graph that is fine for being able to decide what the domain is. And then we'll be all done. So here is if I had my x-axis right there, not perfect, but there it is, it's fine. Notice that I have x values on this thing. I told you they're going to go on forever in that direction, right? So that means we've got from negative infinity, we're going to go all the way to x equals 2. And, oh, I'm writing this down, negative infinity to 2. And we'll talk about how this notation works. And then we're going to go from 2 to positive infinity. That's one way to write this. Another way to write this is, let's say, so here is 2, we're going to we could write the domain is like all real numbers except x equals 2, something like that. Maybe it would be fine since we haven't learned how to write this stuff yet. We could also say x is less than 2. Can we write it like that? I don't know. Probably shouldn't write it like that. Let's not do that. That's ugly. Anyway, that's how you would describe the domain something like this without knowing exactly how to write that out yet. Something like this would be sufficient. All the numbers on that x-axis are included on this graph except for x equals 2. And if you want a little bit further information, look at this summary. Here it is. Whoa, you could read all about it here. That is a lot to read. And we have done lesson 10. Nice work, everybody.